online class. Our topic is Vibrational Modes of Analysis Using Group Theory by Dr. Jenish Paul, Assistant Professor, UC College, Alva. Welcome, sir, to this session. We have an eminent faculty here with us, Dr. Jenish Paul. He has his doctorate in polymer chemistry from Cochin University of Science and Technology. He has more than 10 years of teaching experience. He has also worked as a research fellow in an ISRO Respond project. He has done many publications at national and international level, and some of them have won many awards. And the Best Paper Award at national seminar is one of them. Dr. Jenish sir, we are so grateful to have you here for this session. Let me hand over the session to you, sir.
Okay, thank you, Ramya, for the nice introduction. So, good afternoon, everybody. So we have discussed several applications of group theory. In the last semester, we have discussed the application of group theory to symmetry adapted linear combinations like molecular orbitals. So this semester, we have to study the application of group theory to spectroscopy, and also we have to apply this group theory to hybridization. Okay, so before going to my session, these are the prerequisites. First, you know about the determination of point groups. You have to understand the matrix representation of symmetry elements, and you should have some knowledge about the reduction formula. Okay, so let's start our session. So I am going to start the session of this vibrational modes of analysis, and we are applying this group theory into these vibrational modes of analysis. So I'm following these 5 steps for this vibration modes of analysis. First step, we have to decide the basis of our molecule. So we will discuss that in later. Then second, you have to assign the point group of the molecule, or you have to determine the point group of the molecule in your question. Then third, you have to generate a reducible representation. Then fourth is reduce this reducible representation into irreducible representations. And fifth is the examination of this irreducible representation. So these are the steps we are going to follow in our discussion. So we have already mentioned that the first step is to decide a basis of our molecule. And in this step, we are using the Cartesian coordinate. So the Cartesian coordinate method is very simple. You have to put Cartesian coordinate into each atom. That is X, Y, Z to each atoms. So here we can see that in the oxygen atom, we are putting X1, Y1, Z1. And in the another hydrogen atom, we are putting X, Y, Z. And also we are putting X, Y, Z to the second hydrogen atom also. So this is actually the Cartesian coordinate basis. The second, we have already mentioned that the second step is the determination of point group. And I have already mentioned that you should be aware of the determination of point group. And I have just mentioned how we can determine the point group. And since water molecule, it's a simple molecule, and it have a C2 rotational axis. And here we can see that there is a 2 sigma V, and there is no sigma H is present. Since these 2 sigma V's passes through the rotational axis, so C2 to sigma V, then we can see that the point group of the water molecule is C2V. So we have determined the point group of water molecule. The water molecule, the point group is C2V. Then step 3 is generating a reducible representation. So first step is the basis. Second is the determination of point group. Third is generating a reducible representation. For the generation of reducible representation, we need 2 steps. So that first step is determination of number of unshifted atom in each operation. So here we can see that the C2V point group, the symmetry elements are E, C2, sigma V XZ, and sigma V YZ. These are the symmetry elements in C2V point group. So we have to determine the number of unshifted atom in each operation. So E means we are doing nothing. So that means these three atoms, that is oxygen atom, hydrogen atom, hydrogen atom, these three atoms are unshifted. So the number of unshifted atoms is 3. Then in C2V symmetry element, we can see that the C2V we are rotating along this axis. When we are rotating this axis, we can see that these hydrogen atoms are shifting. Only the unshifted atom is oxygen atom. So the number of unshifted atom is only 1. Then we are next moving to the sigma V. Sigma V, we can see that this is the plane, and in this plane, if we reflect, we can see that these two hydrogen atoms are changing their position, and the only unshifted atom is oxygen atom. So the number of unshifted atom is again 1. Then when we are moving to the sigma V YZ, sigma V YZ is this plane. This is molecular plane, and here we can see that it passes through the molecular plane, and these three atoms are unshifted, and the number of unshifted atoms is 3. So we have determined the number of unshifted atom. For E, this is 3. For C2, it is 1. Then sigma V, it is 1. Sigma V dash, it is 3. Then second step for the determination of reducible representation is you have to calculate the character per unshifted atom for the representation. Calculate the character per unshifted atom for the representation. Thus you have studied in your previous semester, that is E. For E, so we already mentioned that these are the symmetry elements in C2V point group E, C2, sigma XZ, sigma YZ. This is the matrix representation for E, 1, 0, 0, 0, 1, 0, 0, 0, 1. So in order to determine the character, very simple, we have to sum these diagonal elements. So for the character of E, very simple, we have to sum 1 plus 1 plus 1, that is equal to 3. For C2, this is the matrix representation for C2. And in order to determine the character of C2, we have to sum up the diagonal elements. That is minus 1 plus minus 1 plus 1, that is equal to minus 1. Then the third, we are giving the sigma XZ. Sigma XZ, again, this is the matrix representation. So the character will be 1 minus 1, 1. So sum up, we will get the character as 1. Then sigma YZ, this is when you sum up minus 1 plus 1 plus 1. So we will get a 1. Then we have mentioned that the third step is the determination of reducible representation. And for the reducible representation, we have done 2 steps. First, we have determined the number of unshifted atoms, and then second is the contribution to character. That is, number of unshifted atom is 3, 1, 1, 1, and contribution to the character is 3 minus 1, 1, 1. So we have in the previous slide, we have determined the contribution, and before the slide, we have determined the number of unshifted atoms. So just to multiply this number of unshifted atoms and contribute to the character. That is 3 into 3, 9, 1 into minus 1, minus 1, 1 into 1, 1, and 3 into 1, 3. So this is the reducible representation. So we have completed the third step, that is 9 minus 1, 1, 3. That is the reducible representation. Then fourth step is the reducing the reducible representation using reduction formula. So in your previous semester, you have studied the reduction formula. The number of irreducible representation will be equal to 1 by h is equal to summation of GC into character of I into character of R, where h is the order of the group. That is the number of symmetry elements in the group. That is, in the case of C2V, that is E, C2, sigma XZ, sigma YZ, that is, the character is 4. GC, the number of elements in the class. So in the C3V point group, we can see that this is E2, C3, and 3 sigma V. So that is the number of elements in classes 1, 2, 3, etc. So we will see the later. Then Chi, the character of irreducible representation under operation R. Chi R, the character of reducible representation under the operation R. This is the reduction formula. We are applying the reduction formula to identify the number of irreducible representation present in the reducible representation. So this is our irreducible representation. That is gamma 3n, that is equal to 9 minus 1, 1, 3. This we have determined in the previous slide. So this is the reducible representation, 9 minus 1, 1, 3. Okay, so this is the reducible representation, 9 minus 1, 1, 3. And this is very familiar. This is the character table for the C2V, and this is the character of character of the reducible representation under the operation E, under the operation C2, under the operation sigma V, and under the operation sigma V dash. So for this, I have just put the color code. This red color indicates it is the reducible representation. The green color indicates the character of the irreducible representation, and the black color indicates the GC, that is the number of elements in each class. So in all these, the number of elements in the each class is 1. So that is 1, 1, 1, 1. Okay. So let summation of GC into character of the irreducible representation into character of the reducible representation. So again we can see that GC is 1. There is the character of the reducible representation into character of the irreducible representation under operation C2. So when we put all these, we can see that 1 by 4 is the 1 by H. H is the number of symmetry elements. H is the order, that is 4. So 1 by 4 into 9 minus 1 plus 1 plus 3, which is equal to 3. So the number of A1s present in this reducible representation is 3. And the number of A2 present in the reducible representation is 1. Doing the same operation, we can determine the 1 is 1. The number of B1 is 2, and number of B2 is 3. So we can reduce this reducible representation into 3A1 plus A2 plus 2B1 plus 3B2. Then the fifth step is the determination of vibrational modes. And if there are n number of atoms, we are all familiar that there will be 3n degrees of freedom. And for linear molecule, the number of vibrational modes will be 3n minus 5. And for non-linear molecule, it will be 3n minus 6. And this 5 and 6 is nothing but it is the translational degrees of freedom and rotational degrees of freedom. And we have obtained the gamma 3n, that is total degrees of freedom. So in order to determine the vibrational degrees of freedom, we have to subtract this gamma translational and gamma rotational from the 3n total degrees of freedom. How these translational degrees of freedom can be determined? It can be determined from the character table. So look at this character table. So the translation in 3 directions, that is X, Y, and Z. So here we can see that the X have the symmetry as B1. So Tx will be is equal to P1. The Ty again we can see that, look at the character table, Y, the symmetry element is B2. Then again for Tz it is A1. So the Tx is B1, Ty is B2, and Tz is A1. Similar way, the rotation element is Rx plus Ry plus Rz. Again, we can determine from the character table. So in the third area, there is the Rx, Ry, Rz terms. So Rx, it's B2, Ry is B1, and Rz is A2. So Rx B2, Ry B1, Rz A2. So we have to subtract this from the our 3n, that is 3a1 plus a2 plus 2b1 plus 3b2 minus the translation terms, that is this is the translation b1 b2 a1, and this is the rotational term, that is b2 b1 a2. So b1 b2 b1. So finally we will get the remaining terms, that is the vibrational modes are 2a1 plus b2. And this each irreducible representation corresponds to a single vibration, and the water molecule have 3 distinct vibrational modes. So we are familiar that 3n minus 6, that is 3 into 3, that is 9, minus 6, there will be 3 vibrational modes, and out of these 2 will be have A1 symmetry and 2 will have a P2 symmetry. Then we have mentioned that there are 5 steps, and in the first step, that is decision on the basis of the molecule. So we have start from the Cartesian coordinate method. We have said that we have step 1 is we are using the Cartesian coordinate, then determination of point group, then third is generating a reducible representation, and then we have determined the number of irreducible representation using this reducible representation, and the fifth step is determination of vibrational mode. And in the previous, we have used the Cartesian coordinate method. In this, we are using the internal coordinate method. In Cartesian coordinate method, we are putting x, y, z into, that is a Cartesian coordinate into each atom. Internal coordinate is nothing but it is the coordinates that are changing during vibration. So here we can see that during the vibration, the R1, R2 will be changing. So R1 will be changing and the R2 will be changing. And during the bending vibration, the theta will be changing. The angle will be changing. So these are the internal coordinate of water molecule. That is R1, R2 and theta. And we have to determine the point group. Again, we same this water molecule, the point group is C2V. Then third step is the determine the reducible representation using the number of unshifted coordinate. Here we don't need for the symmetry representation, matrix representation. We are directly using the number of unshifted coordinate. So one second, in the previous method, in the Cartesian coordinate method, also if you take this as the coordinate and we are determining the number of unshifted coordinates, we can again determine the reducible representation. Here we can see that if for there will be 9 in the case of E, the 9 coordinate is not shifting. So the reducible representation is under the E will be 9. Okay, under the reducible representation is 9. And in the C2 operation, here we can see that these hydrogens are shifting. So all the coordinates are shifting. So this coordinate is not contributing. This coordinate is not contributing. And only these coordinates are contributing. And here we can see that Z is not changing the position. So Z contribute to 1. X changes to minus X. And Y changes to minus Y. So here we can see that 1 minus 1 minus 1 it will be equal to minus 1. So that we have already determined using the simple method. This step we have already mentioned is the simplest method. So that's why this is 9 and minus 1 we have obtained. So similarly we can get 1 and 3. So in the internal coordinate method, we are using the simpler method. That is, we are using the number of unshifted coordinates. We don't want to measure the number of unshifted atoms. So in the number of unshifted coordinate in E, we can see that this R1 and R2 is not changing. Since R1 and R2 is not changing, the number of unshifted coordinate is 2. We are taking only the R1 and R2. In C2, here we can see that this is rotating. R1 and R2 will be changed. The number of unshifted coordinate is 0. In the case of sigma V, this is sigma V. So R1 and R2 is changing. So the number of unshifted coordinate is 0. In sigma V dash, here also we can see that this is the molecular plane. So the number of unshifted coordinate is R1 and R2, that is 2. So that is 2, 0, 0, 0. And in the case of bending vibration, this is the case of stretching vibration. This is the case of stretching vibration. And in the case of bending vibration, we are taking only the theta. Then E, theta is not changing. So that is 1. C2, theta is not changing. That is 1. Then sigma V, again, theta is not changing. Sigma V dash, again, theta is not changing. Then determination of irreducible representation from the reducible representation using the reduction formula. So for the stretching vibration, we already mentioned that we are taking only the R1 and R2. Since we are taking only R1 and R2, there is this is 2, 0, 0, 2. And then we are taking the number of A1, it is 1. Number of A2 is 0. Number of B1 is 0. Number of B2 is 1. So finally, the number of stretching modes will be A1 and B2. We are directly obtaining the vibrational modes from internal coordinate method. So this is more simpler than the Cartesian coordinate method. So if you put the internal coordinates, you'll directly obtain the stretching vibration as A1 and B2. That is one having A1 vibration and another have a B2 vibration. So A1 means symmetric stretching and B2 is asymmetric stretching. So for the bending vibration, here we can see that. So for the bending vibration, we have already determined the reducible representation is 1, 1, 1. Is actually an irreducible representation, that is A1. So the bending vibration will have a A1 symmetry. Okay. So this is the internal coordinate method. So we are putting the internal coordinates as R1, R2 and theta. And first we are changing the internal coordinate as R1 and R2. We are taking only the R1 and R2. And we are determining the number of unshifted coordinate, that is 2, 0, 0, 2. And then in the bending vibration, we are taking only theta. The bending vibration, we are changing only 1, 1, 1. The number of unshifted coordinate is 1, 1, 1. Then we are using the reduction formula. We can reduce this using the reduction formula. The number of A1 will be equal to 1. The number of A2 is equal to 0. The number of B1 is equal to 0. And number of B2 is equal to 1. And the stretching vibration will be A1 plus B2. So here in the internal coordinate method, we are taking the coordinates which are changing during the vibration only. Then we are obtaining it as A1 and B2. In the bending vibration, there is no need for the reduction formula since it is actually an irreducible representation, and this will be equal to A1. Next, we can take another example. Sorry. Next, we are moving to the spectroscopy and a symmetry selection rule. So we have determined the vibrational modes as 2A1 plus B2. So the vibration during the vibrational modes of analysis, the vibrational modes have 2A1 and 1B2 symmetry. And we have to use the selection rule whether this transition is allowed or not. So whether this transition is allowed or not is predicted by solving the transition moment integral. And this is the transition moment integral, and where psi a is the wave function of the ground state, psi f is the wave function of the excited state, and t is the transition moment operator, and d tau is the small space. A transition is allowed if the equation is non-zero. So it's very simple. We don't want to evaluate this one. And if the transition moment integral is non-zero, we can say that this transition is allowed. And if the transition moment integral is 0, we can say that this transition is forbidden. So let us consider the infrared spectroscopy. In infrared spectroscopy, we can see that it occurs only if the dipole moment changes in the molecule on absorption. So if there is a dipole moment change in the molecule upon absorption, we can see that this transition is allowed. So if in the infrared spectroscopy, we can see that the transition moment integral takes the form that is psi I mu psi f d tau. This mu is nothing but it is a dipole moment vector, and it has 3 directions, that is mu x, mu y, and mu z. And the dipole moment vector along x-axis can be determined using P1. The dipole moment vector along y-axis can be determined using the character table. And dipole moment vector along y-axis, sorry, this is z-axis, is actually A1. So here we can see that x is P1, y is B2, and z is A1. So for water molecule, this we have in the previously determined using the Cartesian coordinate method and internal coordinate method. We have determined the gamma vibration as 2A1 plus B2. So the final state will be A1 or B2. The final state have the symmetry of A1 or B2. And the initial state, always the initial state will be a completely symmetric state, and that will be A1. So it can take other form as A1 or A1G. So these are two are completely symmetric states, and for initial state psi I must be always A1. So in this we can see that this is psi I mu psi f. So psi I must be always symmetric. That has to be A1. So this is our transition moment integral, and the transition moment integral psi I mu psi f d tau, which is equal to integral psi I. Psi I we already mentioned that it has to be A1, completely symmetric. That is A1. And this is mu. Mu can take the form mu x, mu y, mu z. So mu x is b1, mu y is b2, and mu z is a1. Then psi f, we have already mentioned that psi f is the final state, and final state can take two. That is, in the previously we have determined that it can take the form a1 or b2. And the most interesting thing is all we have to decide whether the symmetry of the appropriate part of the equation all multiplied together to give a non-zero result without having to do integration. So it's very happy to hear that we don't need to we don't want to integrate this. And in group theory language, all we need to decide whether the multiplication of the symmetries gives to a totally symmetric representation. And in the next slide, we can see that if psi f is equal to a1, so this is our in transition moment integral a1 b1 b2 a1 and psi f. Okay, so this is a1 b1 psi f we have taken as a1. Then so this is the direct product we are taking a1 b1 a1. Then next is a1 b2 psi f is a1. So this is actually we are taking a1 b2 a1. Then the last one is a1 and the final state is a1. So this is a1 a1 a1. So then next we have to take the direct product. In the previous semester you have studied the direct product. That is very simple. There is a trick for this C2V point group. If a1 and b1, you will get a b2, and b2 into a1 you will get a b2. So here it is b2. Then b2 into a1 you will get a a1. Sorry, 1 second. So this is a1 into b1 always a1 into which symmetry we will get as b1. So b1 into a1 we will get a b1. a1 into b2, again a1 into b2 we will get a b2. a1 you will get as a1. So a1 into any symmetry you will get as that symmetry. That is a1 into b1 you will get a b1. Again a1 into b1 you will get a b1. b2 into a1 you will get as b2. Then b2 into a1 you will get as b2. Again a1. So in the previous slide we have mentioned that in group theory all we need to decide is whether the multiplication of the symmetries give a totally symmetric representation. So here we can see that in this three products, one is giving a1. So that is as if that is a1 is included in one of your answer, and we can conclude that absorbance due to the transition from the ground state to a1 vibration in H2O will be observed in the infrared spectrum. So this transition from transition to a1 state is observed in the infrared spectrum. For psi f is equal to b2. The second, the vibrational mode is in b2. So b2, here we can see that a1, b1 and the psi f is b2. Again a1, b2 and psi f is b2. a1 and again psi f is b2. So here we can see that this is psi f a1, b1, b2. a1 b2 b2 and a1 and b2. So this is I have previously mentioned that if there is in the C2V there is a simple trick. That is, if we multiply this B1 and B2, we will get is A2. Then A2 into A1, that is A2. Then if we multiply the same, that is B2 into B2, we will get the same. If we take the direct product of B2 and B2, we will get the A1. So A1 into A1, it will be A1. So A1 into A, so again A1 into B2, that is B2. B2 into A1, it will be B2. So if you look at the character table, the direct product is nothing but it is A1 into A2. So if you are taking the A1 into A2, you have to multiply this one. 1 into 1, you will get as 1. 1 into 1, you will get as 1. 1 into minus 1, you will get as minus 1. 1 into minus 1, you will get as minus 1. That is A1 into A2 leads to A2. Then if you take the multiplication of A2 and B1. So, okay, A2 into B1. So we are taking the direct product of A2 into B1. So 1 into 1, you are getting as 1. 1 into minus 1, you are getting it as minus 1. Minus 1 into 1, you are getting it as minus 1. And minus 1 into minus 1, you are getting it as 1. So here we can see that the direct product of A2 and B1 leads to B2. Okay. So here we can see that the direct product of A1 and B1 and B2 leads to A2, and A2 and A1 leads to A2. So this is the direct product, and again we can see that this A1 is included. A1 is included in one of your answer, and we can conclude that absorbance due to the transition from the ground state to B2 vibration in H2O will be observed in the infrared spectrum. That is, the A1 vibrations and B2 vibrations are allowed in the infrared spectroscopy. So this is a fundamental mode will be IR active if the excited normal mode have the symmetry as one of the Cartesian coordinate. So this is the selection rule. A fundamental mode will be IR active if the excited normal mode has the symmetry as one of the Cartesian coordinate. So in our excited state, the excited states have two symmetry elements, that is A1 and B2. And look at this character table. A1 belongs to Z axis and B2 belongs to Y axis. And so these two transitions, these two are in Cartesian, these two are the symmetries of Cartesian coordinates. And so this transition is allowed. And if you obtain a vibrational mode as A2, and there is no Cartesian coordinate is present here, that means if your answer contain A2, and that means this A1 to A2 transition is not allowed in your IR spectroscope. Then Raman spectroscopy, you have seen that this transition moment integral take the form of the psi I, P, psi F, d tau, that is the polarizability tensor. So in this integral, P is one of the following quadratic functions of the Cartesian coordinate. The mu x, mu y, mu z takes the Cartesian coordinate, that is mu x is equal to the symmetry of the x-axis, mu y is the symmetry of the y-axis, mu z is the symmetry of the z-axis. And in this case, we are taking the polarizability tensor factor, and the polarizability tensor factor taking the quadratic functions of the Cartesian coordinate. Okay, so here we can see that the Cartesian coordinate quadratic function yz, xz, yz, x square, y square, and z square. So x square belongs to A1, y square belongs to A1, and z square belongs to A1. Then xz belongs to A2, xy belongs to A2, xz belongs to B1, and yz belongs to B2. Okay. So our final state, again, our final state is A1. Initial state, we have already mentioned that initial state is always a completely symmetric representation, and that completely symmetric representation is A1. So A1, then this is the quadratic function representation, that is B1, B2, A1, A2, and this is the psi F. And we already mentioned A1, B1, A1, that is B1. A1, B2, A1, that is B2. A1, A1 A1, that is A1, and A1 A2 A1, that is A2. So we can see that again our final term contain A1. So that means this is allowed in the Raman spectroscopy. Again B2 is A1 B1 B2, A1 B2 B2, A1 A1 B2, A1 A2 B2. So this will be final product, direct product, final of the direct product. And here we can see that again it contains A1. So the B2 is again Raman active. So we have determined the two vibrational modes A1 and B2. This A1 is Raman active, B2 is Raman active. A1 is IR active and B2 is again IR active. So for a fundamental mode will be Raman active if the vibrational mode has the same symmetry as one of the quadratic functions of the Cartesian coordinate. So in order to understand this IR activity and Raman activity, we are moving to another example, that is the vibrational modes of trans N to F2. So so since the time is constrained, I am going a little bit faster. So we have already discussed all the points, all the steps regarding the determination of vibrational modes. And the point group is C2H. The C2 group is there and a sigma H is there. And generate a reducible representation using the Cartesian coordinate. We are putting the Cartesian coordinate, and here we are taking number of unshifted atoms, and we have to determine the character of the symmetry representation. So here we can see the determination of number of unshifted atom. The number of unshifted atom is, that is in the case of E is 4. The number of unshifted atom in C2, since it is passes through the N double bond N, we can see that all the atoms are shifting. So the number of unshifted atom is 0. Then I means we are moving from this side to this side, passing through the center and this side. Then again N, passing through this side to this side, this. So all the atoms are changing their position. So I is 0. Sigma H. So sigma H, we can see that this is the plane, and this plane contain all the atoms, and so the number of unshifted atom is 4. Again, the character for this representation is equal to chi E 1 plus 1 plus 1 3 C2. This is again the sum of the diagonal elements minus 1 minus 1 minus 1 plus 1, which will be equal to minus 1. The character of the sigma H will be the sum of the diagonal elements 1 1 minus 1. This is equal to 1. And the character of phi, that is minus 1 minus 1 minus 1. This is equal to minus 3. So the reducible representation using this will be is equal to 3n, that is equal to 12 0 0 4. So this is the number of unshifted atom is 4 0 0 4. The contribution to the character, E contributes to 3, C2 minus 1, I minus 3, sigma H 1, that is 12 0 0 4. The next is the reducing the reducible representation using the reduction formula. Again here we can see that this is the reducible representation, that is 12 0 0 4 we have obtained using the Cartesian coordinate method. And this green one indicate the green one represent the character of the irreducible representation, and the black one represents the number of class. Again, the number of class is number of element in one class. This is 1, this is 1, this is 1, this is 1. So then the order of the group, that is 1 plus 1 plus 1 1, that is 4 element is present, so that is again 4. So 1 by 4 into this one, this is 12 minus 0 0 4. So totally we will get 3n as 4g plus 2bg plus 2au plus 4bu. Then the vibrational modes, gamma 3n minus translation minus rotational. So tx ty tz is equal to tx ty is equal to bu plus au. Rx ry raz is equal to bg bg ag, rx ry raz. Okay, so again the vibrational modes will be equal to gamma 3n minus gamma translational plus gamma rotational. 4Ag plus 2Bg plus 2Au plus 4Bu. Then if we subtract all this translational rotation, we will get us 3Ag plus Au plus 2Bu. That is trans N2F2 have 4 atoms. That is 4 into 3, that is 12. 12 minus 6, that will be 6. And so we can see that out of the 6 vibrational modes, 3 is Ag, 1 is Au, and 2 is Bu. And we are discussing the IR spectrum, whether this transition is IR allowed or not. Psi I is a completely symmetric representation. So in the C2H point group, the completely symmetric representation is Ag. And psi F is this we have obtained, that is Ag, Au, and Bu. Ag, Au, and Bu. The IR moment, transition moment integral, there will be dipole moment vector. Mu x is dipole moment vector along x-axis. So dipole moment vector along x-axis is Bu. Sorry, this is Bu. And dipole moment vector along y-axis again Bu. And the dipole moment vector along z-axis is Au. So if the final state is Ag, the final state is Ag, dipole moment vector is Bu, Bu, and Au. X-axis Bu, y-axis Bu, and z-axis Au. The initial state is psi I is Ag, completely symmetric representation Ag, Ag, and Ag. Again, this psi f is Ag. So if we multiply, we can see that we will get Au, Bu, and Au. And we have mentioned that if the direct product leads to Ag, this transition is allowed. But there is no Ag is present in your final answer. That is, Ag is not included in one of your answer. So we can conclude that absorbance due to transition from the ground state to Ag vibration in trans N2F2 will be forbidden in the infrared spectrum. Then psi f is Au. If you take the psi f as Au, the mu x is Bu, mu y is Bu, mu z is Au. This is the initial psi I. This is the law of symmetry, completely symmetric representation, that is Ag, Ag, and Ag. This is your final symmetry psi f, that is Au, Au, and Au. So if you take the direct product, you will get as Bg, Bg, and Ag. So here we can see that Ag is included in your final answer. So that is this transition, that is Ag to Au transition is allowed in the infrared spectrum. Again, Bu. Again, we can see that the final product contain Ag. So that is again Ag to Bu transition is allowed in your infrared spectroscopy. Raman spectra. So in the Raman spectra, we have seen that we are taking the quadratic terms, and so the quadratic terms contains only Ag and Bg. So the quadratic terms contains only Ag and Bg. And psi A is a completely symmetric representation Ag, and psi F we have determined using the normal modes of vibration, that is Ag, Au, and Bu. So for psi F equal to Ag, if you take the multiplication, the polarizable terms have the terms, that is Ag and Bg. That is Ag and Bg. This is our initial state, Ag and Ag. This is our final state, that is Ag. So if you take the direct products, we can see that we will get a Pg. And if you take the direct products, Ag. That is, Ag is included in one of your answer, and we can conclude that the absorbance due to transition from ground state to Ag vibration in trans N2F2 is allowed in Raman spectrum. So Raman spectrum, it is allowed transition in this one. For Au, if you take the direct product, you will get us Bu, and another is Au. So that is, this Ag is not present. So the transition from Ag to Au is not allowed. So here is we can see that again AG to BU transition. This is age not age, no AG is present. So this transition is not allowed in your Raman spectroscopy. So that is in this AU and BU, that is IR active. So this is, we already mentioned that in the IR spectroscopy, this AU and BU is allowed. In the Raman spectroscopy, only AG is allowed. So here we can see that this AU, BU are allowed in IR active, and AG is Raman active. AU, BU is IR active, but it is Raman inactive. AG is Raman active, but it is IR inactive. So we are leading to another rule, that is the rule of mutual exclusion principle. That is, we have seen that the trans N2 F2 have a I. I means it have a center of symmetry. So if a molecule have a center of symmetry, IR active vibrations are Raman inactive, and Raman active vibrations are IR inactive. So this is the rule of mutual exclusion principle. So we have to specify that whether the molecule have a center of symmetry, IR active vibrations are Raman inactive, and Raman active vibrations are IR active. So in this character table, we can see that is X, Y, Z terms. That is the Cartesian coordinate terms belong to AU and BU, and the quadratic terms belongs to AG and BG. That means in the center of symmetry, if there is a molecule have a center of symmetry, the AG and BG vibrations will have a Raman active, and AU and BU vibrations. So the U span symmetry have a ungerade symmetry have a IR activity, and the gerade have a Raman activity. So this is actually the rule of mutual exclusion principle. So let's we can start. We can wind up this session. So we have starts from the Cartesian coordinate method for the water molecule, and the Cartesian coordinate method, we are putting the Cartesian coordinate to the water molecule, and we have determined the point group. Then we have generated a reducible representation using this, and this reducible representation is reduced using a reduction formula, and we obtained a reducible representation, and we obtained the number of reducible representation. Then it is these total degrees of freedom obtained, the translational degrees of freedom and rotational degrees of freedom is subtracted, you get it as the vibrational degrees of freedom as 2A1 and B2. So this is the internal coordinate method. Again, we are getting is A1 and B2. So in the selection rule, we can see that if the transition moment integral is non-zero, we can see that this transition is allowed. And in the group theory, we don't want to evaluate this integral. We just have to check whether the direct product leads to a symmetric representation. So here we can see that the direct product leads to a symmetric representation in the case of psi f is A1. And so this A1 is allowed in H2O. And again, B2 leads to a symmetric representation. So B2 is allowed in your IR. So that is a fundamental mode will be IR active if the excited normal mode have the symmetry as that of the one of the Cartesian coordinate. So this we have mentioned that this is B2 of the symmetry of Y, and A1 of the symmetry of Z. So that is these transitions are allowed in IR spectroscopy. And in Raman we can again see that this A1 has a symmetry of X square, Y square and Z square. B2 have the symmetry of YZ. So again, Raman, this A1 and B2 are allowed. But in the case of trans N2 F2, here we can see that the Cartesian coordinates have only AU and BU symmetry. So that is AU and BU are IR active. And here we can say this is AG and BG, this is Raman active. So this is actually IR active or Raman inactive, Raman active or IR active, and so this is the rule of mutual exclusion principle. Please try NH3 as yourself, and you can any doubt you can contact me in your email address. Thank you.
Thank you, sir. Let us move forward with the QA session. Sir, there is a request from one of the attendees, Genga S. Nair. Could you please explain IR spectroscopy final statement again?
IR spectroscopy finals
Statement. The slide, I think the slide which you have shared regarding IR spectroscopy.
Final statement means the selection rule. I think maybe this one. This is the statement of final statement of the IR spectroscopy. That is, sorry, this is Raman activity. Okay. Fundamental mode will be IR active if the excited normal mode have the symmetry as one of the Cartesian coordinates. So we have to look for. So this is the final state. Your final state is A1 and B2, and you have to look for this whether this A1 belongs to any one of the Cartesian coordinates. This A1 belongs to Z. That is A1 is IR active, and look for the B2. B2 is again we can see that this is the Cartesian coordinate, that is Y. So that is B2 is IR active, and if your final state is A2, and look for the character table, there is no Cartesian coordinate is present, and here we can see that this A2 is IR inactive. So if you obtain A2 as your vibration analysis, and we can see that this A2 is IR inactive. So this is the statement. A fundamental mode will be IR active if the excited normal mode has the symmetry as that of one of the Cartesian coordinates. I think it is clear for you. More clarification is needed.
That's fine, sir.
Okay.
Sir, one question is, I think this is something related to the same question which we discussed right now. How do we know which vibrational modes are IR active?
Okay. So same question we have again discussed. So this is the okay. We can look for the trans and 12 so this will be more interesting. Okay, so this is the C2H character table, and you obtained AG, BU, and AU as the vibrational mode leads to. Okay, we can see that this is the final state you obtain, AG, AU, and BU. These are the final state you obtain, AG, AU, and BU. So you have to look for the Cartesian coordinate. AG, there is no Cartesian coordinate. That is AG is IR inactive. And look for AU. AU, you can see that Z coordinate is there. So AU is IR active. BU, we can see that X and Y. So BU is IR active. And in the case of AG, AU, and BU are IR active, and AG is IR inactive. So whether there is a center of symmetry, we can see that this U span symmetries will be always IR active, and the G will be IR inactive. So in the same way, we can determine the Raman spectroscopy. Look for the Cartesian coordinates, so quadratic function of the Cartesian coordinate. So this AG and BG will be Raman active. AU and BU will be Raman inactive. Okay, I think it's clear.
Thank you, sir. I think we are moving towards the end of the session. Thank you so much, sir, for spending the time with us. It was a wonderful session. Sir, do you have anything to address to the attendees?
So next, we already mentioned that the last thing. So due to the time constraint, I have mentioned that if possible, you just try the NH3 spectrum. Use this same method. We have to Just try the NH3 vibrational modes of analysis of NH3. Okay, so this will be NH3, and the answer will be 2A1 plus E. So it is a there is a little bit complication may arise during the reducible and determination of reducible representation, that is class. So in the C3V point group there will be E, 2C3 and 3 sigma V. So that is number of element in the class in the C3 is 2 and sigma V is 3. So you can determine the reducible representation. You can reduce using the reducible representation, and you will get to A1 and to E. E is nothing but it is a representation corresponds to doubly degenerate state. And if time permits, and if one more session is there, I can explain more this the IR spectrum of the NH3 molecule. Okay, so you will just try as yourself, and any doubt regarding this one, you can contact in my mail address. Thank you.
Thank you so much, sir. We are so grateful to have you here. It was a nice session. Thank you all.
Okay. Thank you. Thank you. Thank you.